Imagine you are at 35,000 feet, flying over the middle of the Atlantic Ocean. Outside your window, nothing but dark water. Yet on your screen, you're streaming a 4K movie without a single buffer. How is that physically possible? Your internet isn't traveling through cables. It is shooting straight up to space. But you don't need to be over the ocean to experience this. Whether you're in a rural cabin where cable never reached, on a road trip in your RV, or even on sea on a boat, your data is rocketing 340 miles up to a satellite moving at 17,000 miles per hour. Today, we are tracing that impossible signal from the antenna on the ground to the laser mesh in the vacuum of space. Welcome to the Starlink data journey. Let's trace the path. It all starts with the dish, that flat white antenna that looks deceptively simple. Inside are over 1,500 tiny antenna elements working together as a phased array. Here's what makes this remarkable. The dish doesn't physically move. Instead, it uses electronic beam steering to track satellites racing across the sky. And here's a fact most people miss. Because the satellites are moving at 27,000 kilometers per hour, the radio waves actually stretch and compress. That's the Doppler effect. Your terminal is doing complex math every millisecond just to catch the shifting signal. The processor works so hard, it generates enough heat to melt snow off the face of the dish. Watch what happens now. The terminal locks onto a satellite. It tracks it across the sky, then seamlessly, invisibly, it hands off to the next satellite. This happens every few minutes. You never notice. Your request shoots up. Destination, low Earth orbit. The signal leaves your terminal and begins its climb. First, through the thick lower atmosphere where weather happens. Rain, clouds, storms. The signal pushes through. Then up through the mesosphere, where meteors burn up and leave glowing trails. Finally, into the thermosphere, where the air is so thin, satellites can orbit without burning up. This entire journey, 550 kilometers straight up, takes just 1.8 milliseconds. Let that sink in. Less than 2 milliseconds to cover the distance from ground to space. Now here's the comparison that matters. Traditional satellite internet. Those satellites sit 22,000 miles above the equator. At that altitude, the signal takes 600 milliseconds just to reach the satellite. Starlink's low orbit? 300 times closer. That's the difference between a video call with frustrating lag and one that feels like you're in the same room. Your data reaches the satellite. Now the real magic begins. Welcome to the constellation. Up here, 9,000 satellites work as a single brain. They're not just relay points. They're a mesh network in space. Each satellite has 4 laser terminals. These aren't radio signals anymore. They're optical links, shooting invisible beams of light between satellites up to 4,000 kilometers away. The speed? 200 gigabits per second, per link. Watch your data hot from satellite to satellite, finding the fastest path to a gateway near your destination. 5 hops, maybe 6, spanning thousands of kilometers, all faster than you can blink. Here's what's wild. Light travels faster in the vacuum of space than through fiber optic cables. So for long distances, routing through space can actually beat undersea cables. This network transfers 42 petabytes every day. That's 10 million movies. Daily. Your packet finds the optimal route. Time to head back down. The exit satellite beams your data back down to a gateway station. These aren't small antennas. Each gateway has a massive dish listening for high-frequency K-band signals from space. There are over 100 of these across the US and over 150 worldwide, each one strategically placed near major internet backbones, ready to inject your data into the fiber network. The downlink? Less than 2 milliseconds. Same speed as the uplink, perfectly symmetrical. Each gateway can handle over 100 gigabits per second. That's thousands of users, all streaming, gaming, video calling simultaneously. Your data hits the fiber network. Watch those packets flow. We're back on Earth. Almost there. Now we're in familiar territory, the terrestrial internet. Your data flows through fiber cables, hopping through routers and network hubs, from the gateway to a regional router, router to an internet exchange point where networks connect, then to a data center, and finally to the server hosting your website. This terrestrial portion takes 5 to 10 milliseconds, depending on distance. Let's add up the entire journey. Terminal to satellite, 2 milliseconds. Routing through the laser mesh, 5 to 10. Down to the gateway, 2 more. Terrestrial routing, another 5 to 10. Total round trip, 25 milliseconds. Your data went to space and back faster than you can snap your fingers, before you could even perceive it happened. So, what did we just witness? A single internet request traveling through one of the most ambitious engineering systems ever built. 9,000 satellites orbiting at 27,000 kilometers per hour. 200 gigabit laser links creating a mesh in the vacuum of space. 1,500 antenna elements in your terminal steering invisible beams. All working together to deliver 25 millisecond latency. To put that in perspective, your reaction time is around 250 milliseconds. This system completed a round trip to space 10 times before you could blink. And this is just the beginning. More satellites launch every week. The laser mesh expands. Latencies keep dropping. The future of internet infrastructure? It's not buried underground. It's overhead. If this breakdown helped you understand the technology, hit subscribe. We decode complex systems like this every week. Thanks for watching. And remember, next time you load a page, it might just have visited space.